Good morning, everyone. So this is lecture 6, and we will be continuing with what we were discussing about nitrogen fixation. And I told you that one of the big things which was achieved by BASF was that they could again go back to the iron catalyst of Ramsay and Young. I mean, not exactly that catalyst, but still, it was an iron catalyst, and that way they got rid of the difficulties which were faced with osmium and uranium. Although Haber's work was great and it showed what is possible, ultimately, of course, BASF had to do something different because otherwise, commercialization was not possible. Okay? And I also told you that the mechanism by which the catalysis occurs was unraveled a lot later. More than 50 years after really this work was done, and it was done by Ertl, and I've sent you his Nobel lecture. Now, and I told you that how important it is to have something unique with you, and I keep emphasizing this because that is really the best way of doing something which nobody else can do. That's very important. It could be a software, it could be an equipment, it could be a chemical. It doesn't matter what, but something unique. Which you have, and all of you should try and it's got to kind of imbibe that kind of special skill. Okay? Now, just to show you what I mean by having a unique equipment, this is the work that Ertl describes in his Nobel Prize, where they were able to show that the oxygen molecule goes and adsorbs on a surface, of platinum. They've taken the platinum 111 surface, and you can actually see the two oxygen atoms from the molecule falling apart. You can see that there's a space between the two atoms. Now that is remarkable because that kind of resolution, where I can start seeing individual atoms from a molecule, was really unheard of at that time. And so obviously he doesn't really give a picture of the nitrogen molecule, but I believe that the nitrogen molecule also does something similar. So this is the level of insight which can be provided if you have something very unique with you. Okay, now just to before I even tell you what is the mechanism, let's just go through how exactly this iron catalyst is made. It's a very interesting structure, and I took it from Ullmann's encyclopedia, where the method is described. Of course, I mean this is a general method. Every company will have variations, and which would be proprietary. Then they won't divulge, all those kinds of details. So what it is that first, just like Mitash had gone to the Swedish iron ore and found that it gave a very good catalyst. So you start with an iron ore, and that iron ore is actually magnetite. This is the one, Fe3O4, which has been found to have the right properties for making the iron catalyst. They carry out a reduction of that Fe3O4, and then they grind it up. And what happens is that all of the magnetite does not become reduced, but a part of it gets, and obviously the one which is closer to the surface, that gets reduced to things like ferrous oxide, which has got the name boostite. Okay, so there was a reduction that took place. Okay, and then these particles are again partially reduced, removing some of the oxygen in the process. Okay, and so what happens is that again, I mean, it gets reduced to iron, all right? And so it's a very interesting structure where the bulk of the substance is Fe3O4. Over that, you have a shell of something like iron oxide, and over that, you actually have a shell of metal, Fe. Okay, so what it says is the resulting catalyst particles consist of a core of magnetite encased in a shell of boostite, which in turn is surrounded by an outer shell of iron metal. So it's very, very interesting, this design. And it says the catalyst maintains most of its bulk volume during the reduction, resulting in a, so obviously this magnetite is very porous. So it says resulting in a highly porous, high surface area material, which enhances its effectiveness as a catalyst. Okay, and then it says that there are other minor components, things like calcium, aluminium, potassium, silicon. Okay, and these are either they help to support the iron and created it with a very high surface area, or some of them are promoters. They actually promote the action of iron. And this promoters is something really which, as I mentioned even during the earlier about the contact process, when you all were learning industrial uh, engineering. And at that time, you would have seen how the vanadium pentoxide catalyst is also supported on various things, and there is in addition promoters. Okay, and but these things are themselves not reactive, to hydrogen or nitrogen, but they promote the action of iron. Now, this is again extremely fundamental, and which Ertl says, and I believe that this is the kind of thing for which he got the Nobel Prize. And so what he did, is that he did not really just say, yeah, this Swedish iron ore is great and fantastic, okay? But knowing that iron, Fe, has three different crystal surfaces, which is the iron 111, iron 100, and iron 110. Okay, so these are the ones you can see. This 110, this 100, and this 111. Okay, and what you can see is the 111 is very lightly packed on the surface. Okay, and what he was able to show from the crystal structure, is that firstly, it must be that the Swedish iron ore, which they from which they got the catalyst, and subsequently they may have got it from other places also, has a greater formation of the iron 111 surface. So that's what you encounter in the better catalysts. Okay, and very interestingly, he was able to show that in this particular case, there is enough space for a nitrogen molecule to actually get in. Whereas if you take the 100 surface, you can put in maybe a nitrogen atom, but you don't have space for a nitrogen molecule. And this is of course so tightly packed, the iron 110, that there's nothing that you can put in the interstices. Okay, I mean it can go and of course sit on the thing, but it seems that the action is really when the nitrogen goes into the interstices. Okay, and I suppose another thing to remember is that of course these crystallographic planes were synthetically produced, but in a real ore, you'll never have these things in pure form. You'll have a mixture of all these things, but probably where the proportions will vary. And probably in the Swedish iron ore, there was more of this. Now, why? How does he know? I mean, one was of course that the structure indicated that that the nitrogen molecule can go and sit over there. Okay, but then he also did an experiment where he estimated the coverage of the catalyst with nitrogen as a function of the nitrogen exposure. You can actually calculate from the volume of nitrogen that how much is really the amount in terms of millimoles, and how many millimoles of this iron do you have on the surface, okay? And what was very interesting was that he found that as per expectation, the 110, the coverage is very low unless you give a sufficient amount of nitrogen exposure. The 100 was better, okay, this one, okay, and as I told you, I mean, because but it wasn't really as good as the iron 111. You can see that even with the minutest of iron exposure, the surface got very beautifully covered with nitrogen, which seems to suggest that that this reasoning is probably correct. That is because of the space that is created and the nitrogen molecules can go and sit in the catalyst, that you have such an excellent exposure. And now what he is basically trying to suggest is that, see, we also said that you need promoters and things like that. Those will be there somewhere, in the structure. I mean, it's not the pure structure. And so it's in a form where it becomes easier then to dissociate the N2 molecule, in the adsorbed state. Okay, and that is really what he was able to more or less conclude, and that's the reason why you require this space. And frankly, I mean, the nitrogen molecule on its own to dissociate prior to adsorption is next to impossible. It's because the dissociation energy is so large. So that was a very significant thing. And the second is, most of the people who used to do studies on surface spectroscopy, typically, these are very high vacuum conditions, okay, or relatively high vacuum where you are injecting some trace gases, okay, but Ertl's equipment also had the ability that he could run these studies with a fairly high pressure of nitrogen, and so because otherwise the question can always arise that what is the relevance of this study to when I'm applying 300 bar pressure. How can you say that the two situations are the same? So he was mindful of that, okay, and so I'll just read out what he's saying. There is a pronounced influence of the surface structure. The most densely packed 110 surface is least active, while the open 111 plane exhibits the highest sticking coefficient and is indeed also responsible for the overall activity of the industrial catalyst. This activity is further enhanced by the presence of the electronic promoter K, which stabilizes the intermediate N2 adsorbed complex and hence increases its dissociation probability. Okay, so that's the role of the promoter. The same sequence in reactivity as found for the sticking coefficient for dissociative nitrogen adsorption under low pressure conditions was also found for the yield of ammonia production at 20 bar pressure. Thus, it is also demonstrated that in this case there exists no pressure gap. So he basically showed it's not really due to pressure. Of course, he couldn't go to 300 bar, but even achieving a 24 bar pressure and being able to carry out these experiments under those conditions, I think was an extremely creditable accomplishment, and all possible because of the special equipment that he had designed. Now, then he, of course, ventured into suggesting the manner of catalysis. Okay, and so the first step is really that the nitrogen has to get adsorbed, okay, and that is the N2 add, and then it dissociates into this, much the same way as I showed you, this kind of dissociation of oxygen, and also simultaneously, and I'm not very sure where exactly the hydrogen is getting absorbed, but the hydrogen likewise also gets adsorbed on the surface, okay, and so that's also weakened up the bond, okay. Now, if you were to look at that, suppose I start with half N2 plus 3 by 2 H2, which is the stoichiometric requirement for ammonia, and if I had to, for example, make N plus 3H, okay, then you can imagine the kind of energy, which will be required, and the same would apply for, you can work out for some of these other systems, what it would be if it was not in an adsorbed state, okay. By comparison, when these are adsorbed, there's actually a heat of reaction, and so you actually get a stabilization. So quite the opposite. You're not obviously feeling that activation energy requirement over here. And then one by one, you can see that it's gone into it's got dissociated, okay, over here. So even that is very, very stabilized, the N adsorption plus 3H adsorption, this is also very stable, and that is all being happening because of the catalyst, okay. And after that, the combinations happen, so it is not as if that it's getting weakened and the hydrogen H2 molecule is going and binding. It's all dissociating and then reassociating, okay, in this kind of a manner, and one by one he shows what is really happening to the energetics, for each of these cases, okay. And finally, of course, you end up forming ammonia, and this is really the actual delta H, which you experimentally measure when nitrogen and hydrogen goes to ammonia. Okay, so this was very seminal because it also helped to we had talked about Emmett, saying that this mechanism is not understood. So Ertl's work actually really shed light on this mechanism. But again, I'm emphasizing that, as I had mentioned to you, it's not as if BASF waited for the mechanism to practice the technology. I mean, they did it in any case. So this is like an icing on the cake, you can say. These kinds of things, of course, are also very crucial. All the things that he unraveled, because if you were designing a better catalyst in the future, naturally those are the learnings that you will keep in mind. That how to bias the surface toward maximum 111 plane, so that you can maximize the effectivity of the catalyst. Okay, then the promoters, how exactly the promoters are interacting with the iron or interacting with these nitrogens in the adsorbed state. Those would be things also very important. I believe that he has slightly glossed over how exactly those things happen. But I think that he has broadly got the approximate mechanism perhaps right. And that's the only way to explain the kind of high activity of this catalyst. Is it all clear to everyone? Any questions? Okay, clear?
Yes, sir.
Yes.
Okay. Okay. Now we will come to the most important part as far as Bosch's work is concerned. And that is something that they really did a lot of work on. after they had basically identified a catalyst. Okay, so they had identified a catalyst. They had also identified that instead of that the best way to obtain hydrogen and nitrogen would be by the steam and air reforming processes. So starting from natural gas, you end up with hydrogen and nitrogen. Okay, and which I'm not going to go through in this particular lecture. Okay, but the third, which is very important, is as he says, the equipment. Okay, apparatus. And this is from his Nobel lecture. Let's see what he says. The successful conclusion of the third task, which is the only one I intend to discuss today in more detail, is related to the apparatus. There were no examples in industry. The only technique, and that of a physical nature, involving high pressures was Linde's liquefaction of air. So that we know. I mean that Linde had been able to apply very high pressures like 200 bar and then carry out Joule-Thomson expansion. But that's a physical process. There's no reaction that is taking place in that. In that sense, of course, it's an easier problem. But here, you're talking about pressure plus a reaction, okay, between nitrogen and hydrogen. And these were completely unknown. There was no high pressure chemistry which was known prior to this. I hope you can see how amazing that in trying to solve a problem, you open up so much. And that's what BASF did. They opened up the entire area of high pressure synthesis. Okay, and so that's important. And it's also very interesting, which I learned from Bosch's lecture. Okay, it says initially the high pressure compressors were a great source of worry. Hitherto, large compressors had only been used in engineering for compressing air. In the main, they were used to produce compressed air for running compressed air locomotives in mines and for Linde type air liquefaction plants. So that's it. Okay? And in fact, this is also very interesting. By the way, this is a technology which has been which is actually even today under consideration. There was a time when Tatas were actually thinking of introducing such vehicles, locomotives and vehicles, where what you really do is that you just introduce a cylinder of pressurized air in your car, and the depressurization is what drives the vehicle. This was especially done in the mines because they did not want any kind of sparking. Okay, like if you have the spark plugs and things like that, because in a mine anything can catch fire. So from a safety point of view, things were run on compressed air, and so that was very well known. Okay, and of course air liquefaction was known. Now this is I'm just mentioning. I'm not going to go through this, but that really they started with natural gas, and finally ended up with a nitrogen hydrogen mixture, and that's really what then was used in the synthesis of ammonia. Okay, and they got carbon dioxide as a byproduct. Okay. Now, so why he says he is talking about the equipment. And that's the part that he devotes maximum time to. Now, I will be actually glossing over this. Okay, I'm not going to explain it in so much of detail, partly because of time, and partly because I don't think that I myself understand it that well. Okay, which you all might be able to understand much better. So after this lecture, and you can look at Bosch's Nobel lecture, and if you feel that one of you would like to, or one team would really like to explain to the class what are all the improvements in design that he made, Bosch and BASF, then that will be fantastic. But just think about it. Now, one of the most important things that we learned from Bosch's lecture, which Haber never told us, okay, is that apparently Haber's equipment. This is the equipment. Okay, this is the equipment that Haber used to use, right? And you can have a look at what is the details of the design from Bosch's lecture. And what we learn is that this equipment used to blow up every second day, and they had a lot of problem when BASF started taking this and trying to do experiments. They found it impossible because there was a hazard, safety hazard, and every time again fixing the equipment was a problem. Okay, so what they did was that they redesigned the whole equipment, and I would love it if one of the teams can explain the precise differences between this reactor which was redesigned and this Haber's equipment. What exactly are the essential crucial differences which made it good. Okay, it was of course a laboratory converter, but it was important that they do it because in doing the work on identifying a suitable catalyst, they had to do enormous number of experiments, and I told you that last time, and that number actually was 20,000. And can you imagine? I mean, unless you have a very very good equipment, how will you do so many experiments? Okay? And they had actually several of these units, which they fabricated, and they were running round the clock. So every time some catalyst was being made, it was being subjected to experiment. There's no other way to say whether it works or not. Okay, and that's how they ended up really identifying the best catalyst. Okay, so let me quickly read this out. Right from the start, this test apparatus was a very serviceable design since the individual tests all took a very long time, as it was particularly important to ascertain the stability of the new catalyst in experiments of long duration. So it's not just a question of an initial activity, which is what I find most of the people reporting, I got this result, I got that result, everything looks great, right? But only when you run it for a long time will you come to know whether it is remains great in the long term. Most of the things fall apart. Okay? We took as a starting point the apparatus used by Haber for his test, and of which I append an illustration. Okay, this one. The contact mass surrounded by tightly packed insulation is in the center of the steel vessel. Okay, so that's what the design is. Vessel which is cooled with ice water. Cooling is required obviously because it's an exothermic reaction and you have to manage the exotherm. The gas lead heating arrangement and temperature measuring device are plainly shown in the figure. And so this is all internally heated. The heating coil is inside. And those are all shown. As this apparatus suffered from many drawbacks for prolonged experiments, it was completely redesigned and finally in this form. Okay, figure 2. 24 of them were in continuous day and night service for years. Okay, and that's how they could do these 20,000 experiments. Otherwise, it's impossible to do. And that's the difference between an industrial laboratory, which is really trying to aim for perfection, and a research laboratory, which let's say is trying to publish a paper. The objectives sometimes are very different. The sense of perfection. Okay, now what happened was even with this, they had problems, which actually became clear to them when they started scaling up, the unit. Okay, and nothing as good as reading it out from Bosch's lecture, so that you can see what he says. The state of affairs was soon to change when we started to build a small converter as a production apparatus. Haber had already attempted something along these lines on a very small scale, but had only run it for 1 or 2 hours when it failed for design reasons. We therefore then built an apparatus of which the chief and for us the most important and interesting part, except for a circulation pump and the ammonia separator, was a contact tube of the shape and size illustrated in figure 3. I'm not showing this figure, it's in his lecture. You can go and look at it, and I would urge one of the teams to actually look at all this. Okay, wall thickness about 30 mm. This tube was heated on the outside, not on the inside. Being cautious, we had housed it in a strong, reinforced concrete chamber far away from all the busy centers of activity, since in the meantime we had also become familiar with the danger of fires and flare back which occur frequently with spontaneous ignition when hydrogen emerges at high pressure. Okay? So you've got hydrogen emerging, from this reaction, and there's always some leakage of oxygen. And you can imagine, all it takes is one spark, and that's it. You can have a massive explosion. The two tubes drawn by Mannesmann had each done service for 80 hours, then they burst. If we had charged them with osmium instead of our new catalyst, the world supply of this rare metal, which we had already bought up, would have disappeared. What he's basically trying to say in what context is that with osmium you could get a somewhat lower temperature and pressure of operation. I mean, in that sense, it was a damn good catalyst. Okay? Maybe that's the reason why Haber did not encounter as serious a problem as what BASF did. They probably operated at higher temperature and pressure because the iron catalyst did not work so well at such low temperatures as in pressure. I'm presuming. Okay, so that's what he's talking about. But what he's saying is, what's the point in talking about osmium? It's not available. There are only a few kilograms in all of the world. So in any case, we have to solve the problem of operating it under the catalytic conditions required for the iron catalyst. I can't go back to osmium. I have to optimize it for iron, which is the mass catalyst that one can produce. Okay, all right. It was found on examination of the burst tubes that they were swollen, and it was apparent that owing to some change of the material, the inner wall had altogether lost its elasticity, and the change had continued until finally the undamaged part became too thin and yielded to the internal pressure. So that's what happened. I mean, I started with quite a thick vessel, but it started getting worn out from the inside. Okay, and finally it gave way. So that's what was happening. This is illustrated in figure 4a. A chemical attack was the first thought. But what could have happened? To begin with, hydrogen seemed harmless. Hydrogen seemed harmless because hydrogen with Fe, there wasn't any work that was reported on that. Okay? Whereas nitrogen was more suspect because people already knew that Fe can form compounds like iron nitride with nitrogen. So that's what they were suspecting. To begin with, hydrogen seemed harmless, nitrogen being more suspect, since according to the available literature, iron nitride was apt to form and was described as a silvery brittle compound forming readily from ammonia and iron. This was apparently, it can form. Chemical analysis showed no trace of nitrogen in the embrittled material. So, although they had suspected it, they said, look, if it is iron nitride, then I will find evidence of nitrogen in that damaged reactor, but they didn't find any. Okay, so they had to rule it out. And it says more detailed information was obtained by metallographic analysis a test procedure then almost unknown in chemical engineering and with which I was acquainted only because I had begun my career as a metallurgist. So now you know that Bosch was a metallurgist. He started as a metallurgist, okay, and so he understood, these materials very well, probably better than most of the mechanical engineers and chemical engineers there, and so and because of his training, he was able to carry out a very in-depth study. The following picture emerged. Now, this is really wonderful. Firstly, they had used stainless steel. Okay, so carbon steel, the only suitable type owing to its mechanical strength, has a structure in which the carbonaceous pearlite, the carbon is present in the form of what is known as pearlite, is dispersed in a matrix of pure iron, ferrite. In the changed inside of the used tubes, the perlite had disappeared. They said there's no perlite anymore, you know, and and the structure had been destroyed by cracking. Okay? And decarbonization of the iron had thus occurred. Okay? So basically, the carbon had got destroyed. Okay, had occurred, and pure soft iron should have been formed. But if carbon had just got destroyed and it had disappeared, then I should have been only left with the iron. That's what they said. But it should have been soft. But what they got was brittle. Okay, so but that was obviously not the case, as the changed material was hard and brittle. In fact, what they found was hydrogen was in fact found to have penetrated the iron and formed a brittle alloy. Okay? In the same way as carbon forms brittle iron carbide with iron. Okay, so basically, that's the kind of thing, like it was like an iron hydride, which was behaving similarly to an iron carbide. Okay, then he says subsequent examination showed the cracking is essentially caused by the decarbonization of the perlite with the formation of methane. Hydrogen reacted with carbon to form methane, which becomes enclosed in the structure under extremely high pressure and together with the mechanical stress on the material loosens the structure. So it was methane, and methane, of course, being a gas and forming a lot of methane, it was creating a tremendous pressure on the surface, and stressing it out, and causing the cracks. So I hope you can see the kind of analysis which Bosch did, and just to get to the bottom of the problem. Is it clear to everyone? Everybody understood?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. Now what was very interesting is, okay, I've identified the problem. How will I solve the problem? They wanted to get into manufacture. So what should they do? Take 1 minute to think and answer.
So we could coat the inner surface with something so that hydrogen does not penetrate.
Oh, inner surface with something. This is a brilliant idea. You okay, I'll write it down. Coat with something. It's a very good idea. Very smart. Anything else? I'm not sure whether they tried it, but remember one thing, that in those days, they had, we are talking about high temperature and high pressure. So to get some kind of a coating material which could do the job, was not going to be that easy. That's for sure. But I think conceptually it's a very, very good idea. Anything else? And they wanted to do it fast. They didn't want to get into deep research.
So can we change the material of construction?
That's a good idea. ultimately that's what was done. But you see, I mean, again, if you try to change the material of construction, means that again you have to go back to fundamental research. Because I mean, they were comfortable with steel. To do research on something, I mean, it would take time, right? It's not so easy to come up with a new material,
Yes, sir.
isn't it?
Yes, sir.
Yeah, so those are the practical issues. Okay, any other thought that comes to your mind?
So removal of excess pressure.
That's
What is
brilliant. But how?
so?
This is really amazing. The answers you all are giving. Wait. I'll just forget. So I'm just going to write it down. Okay, and so I create a bit more space and I can write. So one was student ideas. Uh, Introduce a coating, right?
Yes.
Coating. Then the second was change the material. And the third was can the pressure be released somehow, right?
Or moreover regulated, like
The pressure be released,
regulated.
regulated. Brilliant. Anything else? Brilliant ideas. Anything else that comes to your mind? The reason why I'm asking you is because I can tell you that there was another solution which could be kind of implemented right away. I mean, of course, look, we are listening to the probably the greatest process ever invented. So if you don't think about it, there's nothing wrong because the chances that one would think about it is not so high. It's really a very, very smart. What they proposed is a really practical engineering solution, you know. And so I will read it out because to me it's just so beautiful, what they did. We assume to start with that the diffusion of hydrogen into the iron, the decarbonization of the perlite, and the formation of brittle iron hydride are just unavoidable. He said, look, I mean, we are working with hydrogen under pressure. It's going to go and attack that carbon and form methane and iron hydride and all this stuff, and you're not going to be able to really prevent that. Uh, they they had to be rendered harmless by the modification in design. Now, what that modification in design is that you see the attack by hydrogen was something which was happening. It required both high temperature and high pressure. And as one of you so correctly mentioned, that if we could have regulated the pressure of hydrogen, so that it doesn't really have a very adverse effect on the vessel, that would be great. But on the other hand, the contradiction is that how will I regulate, because I need my 300 bar pressure to carry out my reaction. So, I mean, how will I do that? If from these lectures you don't imbibe anything else, but just imbibe some ways of thinking originally, right? That's all. I would consider that the mission has been accomplished. I mean, that's all. Okay. So what does he say? The wall of the converter serves two purposes. It holds the pressure of the highly compressed gases and provides a gas tight seal. Okay. So one is that I need a gas tight seal. Okay. And the other is the wall must be able to hold the pressure. Otherwise, it'll all burst and explode. Okay. So I have to have both of those functions. Okay? And then he says, what would be the result of separating these two functions and allocating them to different components? Okay? Now, now that you have understood, how could I separate the two functions?
So, in a place we can keep the metal different in the whole reactor sort of a thing,
Yeah,
from where the temperature can be regulated. There can be no carbon in that part of the vessel.
I see. I see what you're saying. In one part, huh?
Yes, either at the bottom or at the top, so that from there the extra pressure can be released.
Okay, okay. All right. Any other suggestions?
Sir, if inlet and outlet pressure from like in the one what gas is being provided and what is formed can be separated out by
Yeah.
somehow,
Uh,
so
no, but
that it won't.
the damage will happen at the inlet. I mean, how would you avoid that? There is a residence time, right?
Yes, sir.
Yeah. I think, something tells me that maybe if I were to leave you for 24 hours, and all you do is think, yeah, and you will propose and you will dispose, you will say, no, it's never going to work, and you'll propose something else, you'll say, again, it won't work, and finally you'll get it. Yeah. And by the way, that is concentration. When you are absolutely 100% focused on a problem and you're obsessed with it, you're thinking, dreaming, all you're thinking is reactor, hydrogen attack, and finally one day you'll say, oh, I got it. Okay? So what he says is it soon proved practicable to do this. That is allocating, separating out the two functions. The very first test converter built on this principle validated this reasoning. The long sought solution consisted in fitting a pressure bearing steel jacket internally with a quite thin lining of soft steel. Mind you, one of you mentioned about soft steel which does not have carbon. Okay, you probably didn't exactly quite figure out how it will be put, but it's brilliant what you said. All right. So I will say that uh, uh, some portion uh, uh, which of reactor which did not have carbon. Right? That's what you were trying to say, something like that. Is that correct?
Yes, sir. Yes, sir.
Yeah. So that's brilliant. What you thought, and in a sense, that's what they're doing. So this is my lining inside. Okay, this is my outer steel jacket, right? And this is where my catalyst and gas streams, etc., are passing. So what happens is the if let's say some hydrogen, has to go, where will it go? I mean, it can only go past the lining. Okay, and what they said is, let the lining get damaged. That's okay. We will change the lining every now and then. No issue. Okay, and by the time the gas actually passes through the lining, it's lost all its spent force. Obviously, it's not going to come out through the lining with high pressure. It would have all the pressure would have got dissipated because it's just diffusing through that lining. Okay, so what it says is the long shot solution consisted in fitting a pressure bearing steel jacket internally with a quite thin lining of soft steel in such a way that as the hydrogen, which of course only diffuses, passes through the thin lining, it is able to escape without building up pressure before it can attack the outer steel jacket at the high temperature. So yes, if some hydrogen went through that lining, I mean, it would still be very hot because the reaction mixture is hot, but it will not be under pressure. So if it then goes and if it goes and meets the outer jacket, it's not going to really cause any very serious harm because it's not under pressure, and
Sir,
it was high pressure which was the problem. Yeah,
sir, so it is like a combination of what I had suggested and what Neelav suggested,
absolutely.
like a coating which does not
Like
have
a
that.
coating, it's instead of a coating, you have a liner.
Yes, sir.
Okay, huh? So that's why I'm saying, your suggestions were very good. Okay, Acha. Then let's see. This is readily achieved, and what it then says is, this is a little bit of more engineering. This is readily achieved by the grooves produced on the outside when the tube is being turned, and by a large number of holes drilled in the steel jacket through which the hydrogen is free to emerge. I mean, after that, actually, my outer jacket job is not to provide a seal for the hydrogen that is being, or the gas mixture that is being done within the liner. The outer jacket is only up to manage the pressure, okay, and so that there's no explosion, nothing goes off, and so what happened was that even when this hydrogen was coming out in the outer jacket, they drilled some holes, to actually allow the hydrogen to escape, because that was not crucial for the inside. Over here, it was not crucial. No? Okay, so the hydrogen has already passed through the liner, so I don't have to worry. Okay, so right at the outset, the thin lining tube fits tightly against the jacket under the high pressure, and later, when it has become brittle, there is no way of expanding it again so that no cracks occur. So they had fitted so snugly, that it could not actually expand against the jacket, and so it did not create any cracks, and diffusion losses were minimal, So not that a hell of a lot of hydrogen really went through, because if it had cracked, of course, then the interior pressure would have been felt by the exterior jacket, but they created it in a way that the liner slowly wore out, but it didn't crack. Okay, so that's what they did. The second thing that they also did was that, as the hydrogen was passing from the inside to the outside, means coming out from the liner and heading towards the jacket, they started flushing nitrogen, and this is why they created the grooves, they were basically passing nitrogen, and flushing out the hydrogen before actually it came in contact with the outer jacket. So the outer jacket again became doubly protected, and that was the solution which allowed them to build large plants with just this concept of segregating the two functions of a reactor, of the converter. Is that clear to everyone?
Yes, sir.
Yes, sir.
Yes, sir.
In every case, whenever you see an invention or some smart idea or something, always try to relate it with your own work, and you'll be surprised that if you sort of dig deep enough, you'll find that you have actually in some situation thought of something similar, maybe in a totally different context, but the approach may not have been so completely unrelated. It's always a lot of fun to do that. You feel it's also good, because it forces you to think. whenever you ask the question, did I do something that is similar? And I was telling you about something in a completely unrelated context, but then, I just thought that maybe there is a relationship. And so what happened was that, at that time we were producing biodiesel, and that was the first biodiesel which you could actually pour into any car and run it 100% biodiesel. And it was a very pioneering work which was done along with Mercedes Benz. And it was written about all over the world as something very pathbreaking. It's not difficult to make the crude biodiesel, which was just a transesterification of uh, some oil. Okay, uh, but the real catch was that how do you purify the crude biodiesel? And I'll mention to you a bit more on a final solution which we arrived at. But what I'm going to tell you is about an interim solution. But it was important because it solved the problem at a time when it was required. Because if that had not been done, then the entire interest in the project might have disappeared. So what is there is that in the crude biodiesel, apart from, of course, the biodiesel, there are many impurities, which are present. For example, glycerol, which is the byproduct of transesterification, and then you have got a catalyst which is used. There are traces of solvent. Then there are a few other things, which are soluble in water, but if they are present in the biodiesel, it will have a very bad effect on the car. So you can't run it. Okay. So of course, the most obvious thing to do is to try and wash out the biodiesel, which is not really water soluble. You try and wash out the impurities with water. But the problem was that because during the transesterification process, some amount of saponification also takes place. And any saponification, it was a base catalyst. Any saponification will give you a soap, right? And so, when you're putting water along with the biodiesel, so you've got a perfect recipe for an emulsification. Because naturally, you've got an oil phase, you've got a water phase, and you have got a soap, which is an emulsifier. And what do you normally do? Normally, what one does is that you put the water, you've got oil, and you shake it up well, okay, and obviously try to transfer all the water soluble impurities into the aqueous phase, and hopefully that will clean up the biodiesel. Okay, but the problem is that because of this emulsification, which also takes place, so it becomes a mess, and it's very difficult to break the emulsion once you have formed the emulsion. So the issue was that any emulsification process, unless it's a micro emulsion, it requires that you have to do some work. Okay, so obviously when you're shaking, you're actually doing some work. Okay, and that is the energy that is being utilized in effecting the emulsification. So what I was thinking was that, is there any way to segregate the two things? One is an undesired thing, which is that shaking the oil in the aqueous phases is good for removing the impurities. Okay, but it is bad because it causes emulsification. So if you were left with this kind of a problem, and if you have to look at segregation from everything that I told you, what might you consider doing? How can I avoid the unfavorable stuff and try to achieve the favorable objective of removing?
So to not shake it means we will not.
Yes, very good. Very good. Do not shake it. Okay, so that is actually what was done. I mean, like if you have, let's say you take a measuring cylinder and you have got your crude biodiesel. Its density is lower than that of water, and then you can put water on top. Okay, and we also had a device whereby we could keep the two phases partitioned, like a valve, some kind of a butterfly valve or something, and then you kind of just take out that valve or open the valve, and so what happens is that the only flow of water that takes place is the flow under gravity, and so obviously the water will move towards the bottom, and the oil phase will be on top, and in going through the oil phase, it of course removes all the impurities. It's not as if there won't be any shearing. There will always be a gravity-induced shear. So that will happen, but that extent of shearing is a lot less than if you are shaking the flask, let's say. Okay, and so in fact, it was partly successful that most of the impurities could be removed. Okay, not entirely, I must tell you. Okay, but most of it could be removed. Okay, and the problem of emulsification was relatively much less. It's still, even with the gravity induced shear, there was sufficient amount of work which gets done that you can actually does lead to some small amount of emulsification very close to the surface. So you can actually skim it off, that portion, and the rest of it then looks all right. And so that was actually the first material that was given for evaluation, and it was found to be really almost approaching the desired level of purity. And later on, of course, when I'm talking about the TRIZ methodology, I will tell you about a better solution which was devised. So this actually finally was not done, but it was very, very crucial at that point of time because time was of essence. I mean, we had to find a short-term, quick solution. Okay? And so this is another case of segregating two functions of shaking, and kind of coming up with a different solution. Is that clear to everyone? Did you understand
Yes,
it?
sir.
Yes,
Yes,
sir.
sir.
Okay. Okay. All right. So let me now, in fact, this was the other thing that you all had mentioned, some of you. And that was the first idea that came to you all, that why not change the material, from whatever steel they were using. And I told you that this is, it will take you into, again, like discovery research, because you'll have to figure out, how to do it. And so that, of course, is very important, but it would be a relatively more long-term solution. Okay, but it's not as if BASF was not doing it. Okay, BASF actually were very focused also on trying to find a better material of construction than the kind of steel that they were using at the time. Okay, and also there was another reason why it was important, because in every place, in all parts of the reactor, they found it difficult to put a liner. So there were some parts of the reactor which where you had to look for a different kind of a solution. So I'll just read out what he says. I have already stated that in what are termed refined steels, we found a suitable material which finds particular application at points in apparatus which are awkward to protect by lining. Okay. Figure 21 follows for comparison with iron ingot steel. Refined steels are merely carbon-containing iron alloys, e.g., with chromium, tungsten, and nickel. Okay, that's what typically these refined steel are. Okay, and then it says examination showed that pearlite nickel steel is very sensitive to hydrogen attack. In many cases, more sensitive even than ordinary ingot steel. The sensitivity rises with increasing nickel content. We know, for example, that nickel is an excellent catalyst, for example, for hydrogenation. And so obviously hydrogen is soaked up by nickel. It's very efficient, okay, in absorbing hydrogen, and that actually helps to promote the subsequent attack on the carbon, which led to destruction of the carbon and formation of methane. Okay, so but on the other hand, you need nickel for the kind of properties, the strength of the material, the steel. Okay, so what they decided was not really to remove nickel. Okay, but what they said is that can we add something, to this steel, which will counteract the problem which is posed by nickel. That's really the way in which they approached it. Okay, and he says this influence of nickel can be offset by the appropriate addition of alloying metals such as chromium, tungsten, molybdenum, etc. So it was not to take out nickel, but to add something which will counteract the effect of nickel. Okay? But still help in maintaining the properties. Okay? And then he says the graph figure 22 shows, for instance, a tungsten content of 2% is insufficient compensation. Okay, and that the loss of strength and expansion increases strongly with the nickel content. Okay, so what they did was they added some tungsten, okay, into this steel, and what they were measuring two things. They were over here. They were measuring the loss of strength. Okay, this is the loss of strength, I think. Okay, and this is the loss of extension. So it loses its ductility. The material, and you can see that even when they put let's say 2% of tungsten, there was a substantial decrease, okay, in the properties, especially as the concentration of nickel, increased, which they could not, and they needed high levels of nickel for the particular strength of these materials. So it was unsatisfactory. After that, what they did was they varied the concentration of tungsten, okay, and at 5% tungsten concentration, what they found is that the changes are minimal. So this was a real breakthrough for them. So they were actually then able to have this kind of an addition of tungsten, which under those conditions of use, it did not really affect the properties of the material substantially. In other words, the pearlite structure was more or less retained, okay, in that. So this was a huge breakthrough, and obviously, in particular parts of the reactor, they decided to incorporate this kind of a different kind of a material, okay, and maybe they actually used then both concepts. They used a liner for the bulk of it, and for particular places like the neck, etc. they had this special kind of steel which they utilized. Is that clear? All understood?
Yes, sir.
Okay. All right. Now, this is the other thing, very, very important, which Bosch teaches us. As I told you, I mean, they were BASF was a great company and had such landmark processes like the contact process also developed there. And as we have discussed, both the contact process as well as the Haber process are both exothermic processes. And in the contact process, we have seen how heat is extracted out, very efficiently, and they evolved a compromise solution where you allow the reaction to take place under adiabatic conditions for to a certain extent. Then you extract the heat. Then you again put it back into a second bed of catalyst. Again, let the reaction take place. Again, extract out heat. And that way, rather than the extreme of doing it under an isothermal condition, and on the other extreme, doing it entirely under adiabatic conditions, both of which are unacceptable. Okay, so this was a great compromise, and all they did was they really borrowed the ideas from the contact process, and that was developed by this person, Nietzsche. Okay, and he's the one, and you can see what Bosch says. Based on Nietzsche's well-known design for the sulfuric acid contact process, the converter was conceived as shown in figure 27. Okay, so this is the converter for the ammonia synthesis. The design reproduced here for the ammonia converter incorporates all the characteristics of the best modern tube converter, the heat of reaction being removed as evenly as possible. Now, what I want you to do is that when you all make your presentation, I really want you, because so many of you come from a strong engineering background, that I really want you to cover in a little more detail these kinds of improvisations which Bosch mentions, okay, and just so that things that I have glossed over, I'm not really explaining to you what is the design of this converter here, okay, but I would like you all to read and try to understand as well as you can, okay, and explain what exactly is the details of the design of this particular converter. Okay, so both the overall reactor which was devised, how exactly does it look, okay, and this particular heat extraction methods, which were very efficient, how exactly it is done. Okay, so I would say that what Bosch's lecture, teaches us is all the smart things that a company can do to cut short, on the development time. Okay, so one is that you learn as much as possible from whatever already has been done. There's nothing better than that. Learn, and many times you'll find that you really just have to adapt a learning. You don't have to create an entirely new learning. So that's very important. And again, the for example, the ideas on promoters, etc., which they had developed for the contact process, they utilized again in the development of the catalyst, the ion catalyst. So there was a huge learning, okay, which they could tap into, and this is something that I would suggest that all of you, first question that you should ask is, what is already there? No, and you'll get a lot of inspiration for that. Another very important thing that they did was that realizing that because you're operating at a high temperature and pressure, and the normal boiling point of ammonia is around minus 33 degrees centigrade. Okay, and so they realize that when although I'm operating at very high temperatures, but because I'm also operating at a high pressure, so there is not too much of cooling that one needs to do to be able to condense the ammonia, under that pressurized condition to liquefy it, so that finally, you can take it off as liquid ammonia. Okay. Now this is again very very beautiful because you see you are taking advantage of the process as it exists, okay? And you're trying to maximize the advantage, that you can derive out of the process. The only advantage is not necessarily the only the reaction which you're carrying out. Okay, that's the primary advantage of doing it at high temperature and pressure, because the catalyst is most effective under those conditions. But that also helps you, because it's pressurized, that it helps you to keep the ammonia in a liquid state with minimum additional energy input, and so that was a great thing, because you also did not have to expose then the product mixture to moisture at all, and so you could just take out the liquid, the ammonia, because that's the only thing that will liquefy. Okay? And whatever was the unreacted nitrogen and hydrogen, you could just again recycle along with fresh charge. And because we have seen that moisture is detrimental to the reaction, and it needs to be removed. By doing this, you achieve so many things. I mean, one was that you could drive the equilibrium to the right because all of the ammonia has been taken out. So it helps in the subsequent conversions. Okay, and the second is that there is no exposure to moisture, and the third is that you are able to achieve all of this with minimum additional energy input. Okay? Because you're taking advantage of the fact that as you increase the pressure, the boiling temperature goes up. So and it goes up sufficiently that I really don't need to do massive amount of cooling. Okay. Is that clear? Okay,
Yes.
and you can see actually, you can actually just cool it with just water. Okay, and so that level of temperature reduction that you can achieve is adequate to actually liquefy your ammonia. Okay, so that's a huge thing. Okay, and later on, of course, once you have obtained the ammonia, then naturally, you will keep that under refrigerated conditions and till you have transported it. Okay, and that's how liquid ammonia is transported. Okay. Okay, now in fact, this is another thing. What they realized is that you cannot just focus on feedstock, catalyst, okay, reactor. That there's more to look at. Okay? Like for example, process parameters like the temperature, okay, of the reaction. Okay? How much ammonia is being formed? Okay? What is the pressure of this entire system, because you need to monitor the pressure and how the pressure is changing because it's reacting. So you need to know all that. Okay, and what they had identified was even traces of oxygen can be very detrimental, to the whole process, because we have also seen, that oxygen, of course, also is very dangerous because it can react with hydrogen and form water and create a explosion. Okay, and also, the entire process of steam and air reforming, which is what was used to generate the nitrogen hydrogen mixture, although they were trying to make sure that all of the CO is converted into first into carbon dioxide by the water gas shift reaction and subsequently, traces were being reduced to methane. But many times, I mean, some amount of CO might remain. And you know that, for example, iron carbonyl, okay, can form, and it can completely mess up the entire reaction. Okay, so he says that that they actually developed all of these sensors, in-house, okay, in BASF, okay, because it was so critically important for the entire process. Okay, so whether the process is economical depends entirely on smooth continuous operation. It took BASF years to reach that point. Of particular assistance were the monitoring instruments, since it was possible to follow the events in the converters only by continuous recording. Okay? So this was probably also the first example, of this kind of online sensors which were used to monitor, which today is absolutely routine. Today also you need not probably, invest your own R&D in this, because there will be many other companies who specialize in these very niche areas. Okay, so now the new ability which you must have is your ability to be aware of what is going on, what could be, who are the people you might be able to contact, to source things. Okay, so which otherwise BASF did entirely in-house. But today it would be rather foolish, to do everything in-house. You will try and outsource, or try and bring in, okay, many of the things that you will require, and your innovation will really be about assembling all of these different things, and effectively ultimately forming the perfect solution which you desire for your particular work. So there will be a complete change today from the way people worked earlier. It also, I think, will make things a lot easier. So please do keep that in mind. You must be aware of everything. What is important is that you, as technologists, must be able to identify the perfect solution. you know, and forget about whether you have it or not. What is the most desirable thing to do? If the most desirable thing is that I need to have 10 different sensors, then so be it. Then you go and find out, who are the people who might be able to provide you, with whom you might be able to work to develop some of these. If some of these you need to develop in-house, so you kind of work those out. So you don't compromise on the perfect solution. You identify the perfect solution, and then you may want to do compromises here and there to some extent, and to some extent, of course, you will network with others. Okay. Now, that's not all. Look at again what they did. You see, once they had made ammonia and they realized that the byproduct that they get is carbon dioxide, okay, from this entire process, okay, and they did not want to just let go of the carbon dioxide. Okay. So, and the other problem is, of course, it was already known, for example, that I can react ammonia with sulfuric acid and make ammonium sulfate, which would have been an acceptable fertilizer. There's nothing wrong with it, but it again means expenditure on sulfuric acid to make ammonium sulfate. And so they knew that urea is really can be broken up as you can look at it as ammonia plus carbon dioxide. Okay? And so, and mind you, the second process had already been developed by a Russian in 1870, long before Bosch and all work. And what was the reaction that these people had found? They had found that you can take the ammonium carbamate. Okay, so they knew, they had done some reactions, and they were able to, under certain conditions, convert it into urea. Okay, so this reaction was known. Okay, this reaction. and it provided the spark to Bosch, okay, and this other person called Miser, you know. And what they said is that, look, what is this? This is really what is this? This carbon dioxide, okay? And this is it's like two ammonia, but one is NH2 and one is NH4. So I can just write it as a reaction of 2 moles of ammonia reacting with 1 mole of carbon dioxide, and in principle that I can write ammonium carbamate. Okay? And that's what it was known that you can convert into urea. So then they went about, trying to see, okay, if they can ammonium carbamate from ammonia and carbon dioxide. And the motivation was that carbon dioxide, I'm getting it right there because I separated it out, from the initial reactant mixture, to be left with ammonia and nitrogen. Okay? And I made ammonia. What better thing to do than combine the two and make urea? And look at the other advantage that ammonia is a gas, or a liquid. You cannot apply it unless you react it with sulfuric acid or something and convert it into a solid. How will I apply it in the field? But urea is a solid, and it makes use of their byproduct carbon dioxide. So what a fantastic, way of thinking of the problem. So instead of letting go the CO2, they started doing, and what better thing than to do than that, that they have high pressure equipment. They are no longer constrained to do reactions under ambient pressure, So they pressurized, the ammonia and the CO2, and you can also see that the pressure will help to drive the equilibrium to the right, because you've got 3 moles getting converted into 1 mole. Okay? And so they were able to finally come up with a high pressure process, okay, for production of urea, okay, and solve the problem in its entirety. It's just astonishing, the way they looked at, the entire problem.